Hello, welcome to my channel. Before proceeding to study, please subscribe to my channel. Today, we will explore the fascinating world of basic electrical and electronics engineering. We'll dive into key concepts like basic definitions, magnetization characteristics of ferromagnetic materials, self-inductance and mutual inductance. Slide 1. Basic definitions of magnetic circuit elements. Let's begin with the foundational concepts in a magnetic circuit. A magnetic circuit is a closed path through which magnetic flux flows, similar to how electric current flows in an electrical circuit. 1. Magnetic flux, phi. Magnetic flux refers to the total number of magnetic field lines passing through a surface. It's measured in Webers, Wb. Think of it like the total quantity of water flowing through a pipe. 2. Magnetic flux density, B. It is the flux per unit area of a magnetic field. B equals phi divided by A, where A is area. Measured in Tesla, T, it tells us how concentrated the magnetic field is. 3. Magnetomotive force, MMF. MMF is the force that drives magnetic flux in a magnetic circuit, similar to how EMF, voltage, drives electric current. MMF equals N times I, N is number of turns, I is current. Unit is amperes turn, at. 4. Reluctance, R. This is the resistance offered by the magnetic circuit to the magnetic flux. It is similar to resistance in electrical circuits. R equals L divided by mu times A, where L is length of magnetic path, mu is permeability, and A is area. 5. Permeability, mu. Permeability is the measure of how easily a material allows magnetic lines to pass through it. Higher permeability means lower reluctance. 6. Permeance. It is the reciprocal of reluctance. Just like conductance is the reciprocal of resistance. 7. Comparison with electrical circuit. You can think of magnetic flux as analogous to electric current, MMF is voltage, and reluctance is resistance. This analogy helps in analyzing magnetic circuits. Example. A coil of 100 turns carrying 2A produces an MMF of 200 at. Significance. Understanding these basic definitions helps us analyze complex magnetic systems like transformers and motors easily. Slide 2. Magnetization characteristics of ferromagnetic materials. Now, let's explore how magnetic materials behave under magnetization, especially ferromagnetic materials like iron and steel. 1. Ferromagnetic materials. These are materials that can be strongly magnetized and retain magnetism. Common examples: iron, nickel, cobalt. 2. B slide H curve, magnetization curve. It shows the relationship between magnetic field intensity, H, and flux density, B. Initially, B increases sharply with H, then it saturates. 3. Saturation. Beyond a certain point, increasing H does not increase B significantly. The material is said to be in saturation. This is important in transformer core design. 4. Retentivity. It is the ability of the material to retain some magnetism even after the magnetizing field is removed. Useful in making permanent magnets. 5. Coercivity. It is the reverse magnetizing force required to reduce the residual magnetism to zero. Indicates how difficult it is to demagnetize the material. 6. Hysteresis loop. When a material is magnetized and demagnetized repeatedly, it forms a loop on the B slide H curve. The area inside the loop indicates energy loss per cycle. 7. Soft vs hard magnetic materials. Soft materials like silicon steel have low coercivity and hysteresis loss, ideal for transformers. Hard materials like steel have high coercivity, ideal for permanent magnets. 8. Energy loss. The energy lost in the form of heat due to the hysteresis effect is called hysteresis loss. This is critical in alternating current (AC) systems. Example: A transformer core made of soft iron is chosen to reduce hysteresis loss and improve efficiency. Significance. These characteristics help in selecting suitable materials for different magnetic applications. Slide 3. Self-inductance. Let's now understand inductance, a property unique to magnetic circuits with coils. 1. Inductance. It is the property of a coil to oppose any change in the current flowing through it by generating a back EMF. 2. Self-inductance, L. When the changing current in a coil induces an EMF in the same coil, it's called self-inductance. L equals N squared times mu times A divided by L. 3. Unit. Self-inductance is measured in Henry H. If 1 A current change per second induces 1 volt EMF, the inductance is 1 Henry. 4. Factors affecting self-inductance. Number of turns, N, more turns, more inductance. Area, A, of coil. Length, L, of coil. Permeability, mu, of core material. 5. Physical meaning. A coil with high inductance will strongly resist sudden changes in current, which is useful for smoothing circuits and energy storage. 6. Example. A 200 slide-turn coil on a soft iron core has higher inductance than the same coil on an air core, due to higher mu. 7. Energy stored. A magnetic field stores energy. Energy, A, equals 1/2 times L times I squared. Significance. Self-inductance plays a vital role in design of chokes, filters, and transformer windings. Slide 4. Mutual inductance. Now, we'll understand how two coils can affect each other via magnetic coupling. 1. Mutual inductance, M. It is the ability of one coil to induce an EMF in a nearby coil due to changing current in the first coil. 2. Definition. If current in coil 1 changes and induces voltage in coil 2, the mutual inductance M is defined as M equals N times phi divided by I, where N is turns in coil 2, phi is flux linking coil 2, I is current in coil 1. 3. Unit. Same as self-inductance, Henry H. 4. Coupling coefficient, K. It indicates how effectively the two coils are magnetically linked. K equals M divided by square root L times L, where L and L are self-inductances. 5. Perfect coupling. If all the flux of one coil links the second coil, K equals 1, ideal case. 6. Poor coupling. If very little flux links the other coil, K is near 0. 7. Applications. Transformers, step slide up and step slide down voltages. Wireless chargers. Signal transmission. 8. Example. In a transformer, a changing current in the primary coil creates a changing magnetic field that induces a voltage in the secondary coil, based on mutual inductance. Significance. Understanding mutual inductance is key to working with transformers and AC machines. Slide 5. Differences between magnetic and electrical circuits. Let's summarize some key differences between magnetic and electrical circuits. 1. Driving force. Voltage drives current in electrical circuits. MMF drives flux in magnetic circuits. 2. Current vs flux. Electric current flows in wires, magnetic flux flows in core material. 3. Resistance vs reluctance. Opposition to current is resistance, opposition to flux is reluctance. 4. Energy loss. Electrical, I squared R loss, magnetic, hysteresis and eddy current loss. 5. Source. Current needs continuous supply, flux can remain, remanence. 6. Measurement. Electric current measured in amps, flux in Webers. 7. Material. Conductors, like copper, for electric circuits. Magnetic materials, like iron, for magnetic circuits. 8. Insulation. Needed in electrical circuits, not needed for magnetic flux path. 9. Nature. Electric current is actual flow of electrons. Magnetic flux is an abstract concept, lines of force. Importance. These differences help students understand that while the analysis techniques are similar, the physical nature is quite different.